Hi all, up to this point we've applied Newton's second law with just one mass, moving left or right or up or down or in two dimensions. Now let's take a look at how we deal with applying Newton's second law to systems with two or even more masses. So let's just start right out with an example problem. Here we go. We have, let's say, two masses hanging in an elevator. And for simplicity's sake, let's say it's the same mass. And they're hanging by these strings. So we're going to say that we've got the tension in the first string, the upper string, and the tension in the lower string, T1 and T2. And let's further say that this whole system is accelerating upward with some constant acceleration A. So the question we want to ask ourselves is, what is the tension in each string? And the first step, as always, is to draw Freebody diagrams. So we start with the bottom block. And on the bottom block, we have mg going down, and we have T1 going up. T1 bigger than mg because this block is accelerating upward. And now for the top block, we draw our Freebody diagram. And again, we have mg going down. We also have the T1 from, oh, sorry, I labeled it wrong. This should be T2. We also have the string, that lower string, pulling down on the upper block. And that should be just as big as it was pulling up on the lower block. So this T2 going down and this T2 going up are equal in magnitude. And then finally, we're going to have T1, whoa, which should be quite large because it has to counteract T2 pulling down on this block and the weight, and it's also accelerating upward. The block M, the upper block, is accelerating upward. So we know that the sum of the forces acting on both blocks is going to be M times A. So the sum of the forces on the upper block is equal to the upper block's mass times his acceleration. The sum of the forces acting on the bottom block is equal to his mass times his acceleration. If their masses are equal, their accelerations are equal, then we know that the sum of the forces on the upper block should equal the sum of the forces on the lower block. So we fill in the forces acting on, let's start with the lower block because it's a little bit easier. We've got T2 going up, so I'm going to keep that positive, plus the opposite of the weight. So minus mg going down. That's equal to ma. So right away, I could solve for T2. T2 is ma plus mg. Bam. And if we have numerical values for the mass and the acceleration, we can find a numerical answer for T2. And going over here to the other block, we have T1 going up, so he's positive, plus the opposite of the weight. Let's just minus mg plus the opposite of T2, so minus T2 is equal to ma. So solving this for T1, we have T1 is equal to ma plus mg plus T2. But we already solved for T2 over on the other side. T2 is ma plus mg. So let's go ahead and plug that thing in there. And we get the non-surprising result. T1 is equal to 2 times ma plus mg. We're going to have ma plus mg and ma plus mg. The reason that makes sense is both of those blocks are the same mass. So in essence, T1 has to accelerate twice the mass at the same acceleration as T2. So it's no surprise that T1 is twice the force as T2. Now let's look at systems of mass in a little bit different light. We've got two blocks, and they are at rest on a frictionless floor. So we don't have to worry about friction, and they are being pushed to the right. I should say the little m block is being pushed to the right by the force. The 3m block is being pushed to the right by the little block. So there is a contact force right here between the little block and the big block. The little block pushes to the right on the big block pushes back to the left on the little block. So let's do some free body diagrams. We'll start with the one that has the least number of forces on it, the 3m block. So we have 3m times g going down. We do have a normal force on the 3g block going up. And we have a contact force, F sub c, going to the right. On the little block, and those are the only forces acting on the big block. All right. Notice that the force F that I've drawn over here only acts on the little block. You're only pushing on the little block. It's the little block pushing on the big block that causes the big block to accelerate to the right. So on the little block, we have mg going down, and we have the normal force, I'll call it N1, going up. We do have that pushing force F to the right, but we also have that contact force between the blocks pushing back to the left. The 3m block pushes to the left on the m block. And it's the interaction between the F and the contact force that causes the little block to accelerate. So now, what do we want to find out here? Let's say we want to know what the acceleration is of the system. And then let's say we also want to find out what this contact force is. The contact force is question mark. Okay, so now, just to make things fun, we've got a free body diagram for each individual block. Well, what if I just say, oh, well, to find the acceleration, I'm going to consider that these two blocks are together a block of 4m. That's what I meant to write there. Together a block of 4m. What forces are acting on the system as a whole? We've got 4, that was supposed to be a 4m times g going down. We have the normal force going up, and we have that force F pushing both blocks, the system of blocks, to the right. When we consider the system as a whole, because this contact force to the left and this contact force to the right are equal and opposite, they cancel out. They're considered internal forces in the system. So if I just want to find the acceleration of both blocks as a whole, this is the easiest way to do it, because I know that the sum of the forces acting, cannot write today, the sum of the forces acting on the system is equal to the mass of the system, which is 4m, times the system's acceleration. It's very important that you give the whole mass of the system when you do this. So the forces acting are just F. The mass of the system is 4m, and we're looking for the acceleration. So F divided by 4m is the acceleration of the system. And this is going to be to the right. And if we know numbers for F and m, then we can get a numerical answer for the acceleration in meters per second squared. So we've answered the first one up here. It's going to be F over 4m for the acceleration, and we should probably put meters per second squared. And now we want to find the contact force. So to find the contact force, here I get to use my free body diagrams for either boxes. I can use the one for the big block, or I can use the one for the small block. It's easiest to use the one for the big block because there's only one force, Fc, acting horizontally. So the sum of the forces acting on the 3m block are equal to just his mass, 3m, times his acceleration. We just found the acceleration in the previous step. So we've got the only force acting on the block is Fc, horizontally, and that's equal to 3m times the big block's acceleration. The big block's acceleration is F over 4m. So we simplify here, m's cancel, and we see that the contact force is 3/4 of F. And we think back, does that make sense? 3/4 of F. Go back and look at the free body diagram for the little block. If the contact force here is just 3/4 of F, and the pushing force is F, then it totally makes sense because my push force needs to be larger than the contact force. Otherwise, this small block is not going to accelerate to the right. So in the context of the problem, the fact that the contact force is, and I'm going to put newtons there to be specific, the fact that the contact force is less than the pushing force absolutely makes sense, and that's what we want it to be. And we can plug in numbers, we can get numerical answers. All right, so bottom line, when you're looking for the acceleration of the system as a whole, then look at a free body diagram for the masses together. Just make sure that when you plug it into the equation, you've got both masses. When you're looking for contact forces in between two objects, then you're going to just look at the forces acting on one block or the other. Things would work the same if it was 3 blocks. It's just that you would have 2 contact forces rather than 1. All right, that's it. See you next time.